Hello everyone. In this video, I'm going to explain you about the logic gates and the implementation of logic gates. Here you can find many logic gates. This is an AND gate, this is OR gate, this is NOT gate, this is XOR gate, this is NAND, this is NOR, and this is 3-input NAND gate. So to make this logic gates, you can drag switches from here and you can find many logic gates here. From that you can select a gate and the bulb from here. So in AND gate, when both the switches are off, the bulb will not glow. If any one of the switches on, the bulb will not glow. If only when the both switches is on, the bulb will glow. In OR gate, when both the switches is off, the bulb will not glow. If any one of the switch or if both the switches on, the bulb will glow. In NOT gate, if the switch is off, the bulb will glow, but when the switch is on, the bulb will not glow. In XOR gate, if both the switch is on, the bulb will not glow, and if both the switches off, the bulb will not glow. Only when the one switch is on, the bulb will glow. In NAND gate, when both the switch is off, the bulb will glow, or any one of the switches off, the bulb will glow, but when both the switches on, the bulb will not glow. In XOR gate, the bulb will glow only when both the switches off. Other than that, the bulb will not glow. In 3-input NAND gate, the bulb will glow when one switch is on or all the switches off or two switches on, but it will not glow only when all the switches on. This is the logic gates for the half adder, full adder, half subtractor and full subtractor. So in half adder we are using one XOR gate and one AND gate. So A and B is given as an input to the XOR gate, and for this AND gate we are giving A and B as also an input. So when both the switch is off, the sum is 0 and the carry is also 0. If any one of the switch is on, the sum is 1 and the carry is 0. If both the switches are on, the sum is 0 and the carry is 1. In full adder, if all the switches off, the sum is 0 and the carry is 0. If the third switch is on, the sum is 1 and the carry is 0. If the second switch is on and the second switch is alone on, the sum is 1 and the carry is 0. If the third and second switch is on, the sum is 0 and the carry is 1. If the first switch is on, the other switches are off, the sum is 1 and the carry is 0. If first and third switch is on, the sum is 0 and the carry is 1. If first and second switch is on, the sum is 0 and the carry is 1. If all the switch is on, the sum is 1 and the carry is also 1. So now in this half subtractor, we are using one XOR gate, one NOT gate and one AND gate. Here, if both the switch is off, the borrow is 0, the difference is also 0. If any one of the switch is on, the borrow is 1 and the difference is also 1. If the first switch is on, the second switch is off, the difference is 1 and the borrow is 0. So if both the switches on, the difference is also 0 and the borrow is also 0. In full subtractor, we are using 3 XOR gate, 2 AND gate, 1 NOR gate and 1 NOT gate. So you will get the output as an borrow and difference. If all the switch is off, the borrow is also 0 and the difference is also 0. If the third switch is on, borrow is also 1, difference is also 1. If the second switch is on and the third switch is off, borrow is also 0, borrow is 1 and difference is also 1. If both the switches on, difference is 0 and the borrow is 1. If these two switches off and the first switch is on, difference is 1, borrow is 0. If first and third switch is on, difference is also 0, borrow is also 0. If first and second switch is on, difference is 0 and borrow is also 0. If all the switch is on, difference is 1 and the borrow is also 1. These are code converter gates. This is binary to gray code and this is gray code to binary. In binary to gray code, we are using 3 XOR gate, and using these 3 gates, we are going to given 4 outputs. So in this, B3 is directly connected to G3, and this XOR gate uses input B2, B2 and B3. Now if we switch on this, the G3 will glow because it is directly connected. And usually in XOR gate, if one input is 1, the output will be 1. So if both the input is 1, the output is 0. So in gray code to binary, we are using 3 XOR gate, and we are using this, we are going to give 4 outputs. So G3 is directly connected to B3. Here for this XOR gate, we are giving input as in G3 and G2. The output of this XOR gate is connected to this XOR gate as one input, and G1 is connected to this as an input. The output of this XOR gate is connected here, and G0 is connected here as an input. So now if we switch on this, these are also the code converters. So this is BCD to XS3, this is XS3 to BCD. So this logic gate is designed using K-maps. So the K-map equation is, so for the equation for E3 is B3 plus B2 B0 plus B2 B1. In this we are using 2 AND gate and one 3 input OR gate. So here B3 is directly connected. So for this AND gate we are using B2 and B0. For this AND gate B2 and B1. So the equation of B2 is B3 B1 dash B0 dash plus B2 dash B1 plus B2 dash B0. Here we are using two 2 input AND gate and one 3 input AND gate and one 3 input OR gate. So here for this AND gate we are using B3, B1 dash and B0 dash. Here B2 dash, B1, here B2 dash and B0. For this, the equation for E1, B1 B0 plus B2 B1 dash plus B2 B1 dash B0 dash. Here we are using 3 AND gates, one and one is 3 input. Here we are using 3 input OR gate. Now this AND gate is connected to B3 and B0 dash. This AND gate is connected to B1 B0. This is B2 B1 dash and B0 dash. Here we are using two 3 input AND gate and one 2 input AND gate. Here one 3 input OR gate. This AND gate is connected to B1 and B0 dash. This is connected to B3 B1 dash and B0 dash. This is connected to B2 B3 dash and B0. So in BCD to XS3, when all the input is 0, the output is 0. When B0 is 1, E2 is 1. When B1 is 1, E2 and E0 is 1. When B1 and B0 is 1, E2 and E1 is 1. When everything is off except B1, sorry B3, E2, E1 and E0 is 1. So when B2 and B0 is 1, E3 is 1. When B2 and B1 is 1, E3 and E0 is 1. When all the 3 is on, E3 and E1 is 1. When everything is off except B3, E3, E1 and E0 is 1. When when B3 and B0 is 1, E3 and E2 is 1. The remaining combinations are don't care. Now in excess 3 to BCD, this is also designed using K-map. So the equation for E3 is E3, E2 plus E3, E1, E0. So here we are using two AND gates. One is 3 input, the other is 2 input, and we are using 2 input OR gate. Here for this AND gate we are using E3 and E2. Here E3, E1 and E0. For this the equation is E2 dash E1 E0 dash plus E2 dash E1 dash plus E2 E1 E0. So here we are using 3 AND gate and one is 3 input. Here we are using 3 input OR gate. For this AND gate we are taking input as E2 dash and E0 dash. Here E2 dash E0 dash, sorry E1 dash. Here E2 E1 and E0. Here the equation for this is E1 dash E0 plus E1 E0 dash. We are using two input AND gate and one 2 input OR gate. For this AND gate, we are taking input as E1 dash and E0. For this AND gate, E1 and E0 dash. So when we add this, we'll get output. So here for the output of E0, we are taking directly from this. So now we'll see the output. For the first 3 combinations, the output is don't care. And the fourth one is when we switch on these two, the output will be when we switch on these two, the output we get as 0. When B2 is on, the output is B0. When E2 and E1 is on, the output is B1 and B0. When when E2 and E0 is on, the output is B1. So like this, we can get 9 combinations. The others are don't care. This is parity gender logic gate. Using this logic gate, we are going to find the output is odd or even. In this, we are using 2 XOR gate and 1 NOT gate. When everything is 0, it is odd. When C is 1, it is even. Or when B is 1, it is even. When B and C is 1, it is odd. When A is 1, it is even. When A and C is 1, it is odd. When A and B is 1, it is odd. When everything is 1, it is even. So here this is 4 to 1 multiplexer, this is 4 to 1 demultiplexer. In 4 to 1 multiplexer we are using 4 3 input AND gate, 1 4 input OR gate. In 4 to 1 demultiplexer we are using 4 3 input AND gate. Sorry. Now here we are using 4 input and 2 selective input. Here 1 input and 2 selective input. In selective inputs, the input can either be 1 or 0. In this AND gate, we are using I0, S1 dash and S0 dash. Here I1, S1 dash and S0. Here I2, S1, S0 dash. Here I3, S1 and S0. Here we are having two complementary inputs. So when we switch on this, we'll get the output as 1. Here we are having only one complementary input. So when we on the other two, our output will be 1. In I2 also we are having only one complementary input. So we will on the other two. Our output will be 1. In I3 we don't have any complementary input. So we'll switch on all the three. See, our output is 1. This is 4 to 1 demultiplexer. In 4 to 1 demultiplexer, we'll give only one input. The other two are selective inputs. So this input is connected to all the AND gate. Now for this AND gate, we are having three input, that is this is A, this is S1 dash and S0 dash. Here A, S1 dash and S0. Here A, S1, S0 dash. Here all the three are normal input. This is not a complementary input. So here when we switch on this, we'll get the output as 1. So this switch can always be in on. Now we'll switch on this, our output will be 1. For the third input, we are switching on this. So here our output will be 1. For this, we don't have any complementary functions. So we can switch on all the inputs. Our output will be 1. Thanks for watching this video.